All right, welcome everybody to our subnetting workshop. My name is Chris Johnson. I'm the Chief Operating Officer here at Go Cloud Careers. I'm joined today by Mike Gibbs, our founder and CEO, and Leo is with us today. Leo is one of our team members, always behind the scenes, always doing wonderful things for us. So we've got some exciting stuff for you today. We are on multiple platforms. We are on YouTube, we are on LinkedIn, we are on Facebook, we're on Twitter, we're on Twitch. I believe that's everywhere we are today, but we wanted to make this as widely available as possible. So we are so glad that all of you are here. I'm going to hand it over to Mike and let Mike welcome us all in and tell us what all we're going to be doing. And then maybe let Leo say a few words before we get started. So hand it over to you, Mike.
Absolutely. Welcome, everyone. My name is Mike Gibbs, and I'm the founder and CEO of Go Cloud Careers, and I'm excited to be here with you today to talk about networking for cloud computing, whether you consider it to be AWS Networking Training or Azure Networking Training or Networking Skills Training. This is critical information. Today, we'll discuss classful and classless addressing, what is CIDR or classless interdomain routing. We'll deal with some subnetting and variable length subnet masks. These are critical, essential cloud computing technical skills for networking and cloud computing. A little bit about me before we begin. I've now been an architect for over 25 years. I've been a network architect, an enterprise architect, a cloud architect, and a business architect. And I got to tell you, I love being an architect. I think it's the greatest job in the world. But there's other wonderful cloud computing jobs. One thing I'll tell you, if you want to be a cloud architect or a cloud engineer, you must understand the network and the data center. And here's why. The cloud is nothing more than a network and a data center that they rent out to you in a virtualized capacity. And what we do as cloud architects, for the most part, is figure out a plan to take the stuff from the network and the data center to the cloud. So you have to understand the stuff that you're moving. Highly technical term there. I don't like to use a lot of jargon. So, that's what we're actually talking about today. Really essential critical components. Now, I find a lot of people don't understand subnetting. And the reality is, if you don't understand IP addressing, here's what's going to happen. Every architecture will crash and it'll all fail. The networking is the foundation to everything. No network, nothing works. When I started 20 years ago, it used to be common. People would just blame the network. The application's not working, must be the network. The video's not working, must be the network. And here's the reality. At least 50% of the time, they were right. That's how critical these things are. Whether it's Azure that's getting a DDoS attack, it's affecting their network. Or other cloud providers, when they're going down, chances are it's all their network too. So a couple of things before we begin. Give me a hashtag. Subnetting. Tell me where you're at in the chat box. I know some of you have done it, but you're not all here. So today I want to let you know the format of how things are going to be working. I'm going to be talking to you about IP subnetting theory and what it all means. Then we're going to have Leo Paredes from my team, who's over there in Sao Paulo, Brazil. Leo is like the subnet math professor. Talk about someone that's going to get his Excel spreadsheet out. Talk about bits and bytes, and is going to guarantee and make sure that by the end of the day, you understand networking inside and out. You'll laugh at the thought of a subnetting calculator after you hear with Leo's math. Then we're going to come back to me. And when you come back to me, as soon as we're done, here's what's going to happen. I'm then going to talk about applying it again. So it's going to go back and forth between Leo and me. Leo's the senior manager in our organization. He's an exceptional cloud architect, and we're really lucky to have him. He also does a lot of teaching in our cloud engineering program. Leo is deeply technical, and he's got good business skills. So welcome, everyone. Please like and subscribe to the channel if you haven't done so yet. After the session today, we're going to actually do another cloud architect or cloud career question and answer session. We do it every Monday, and yesterday we ran out of time. There were all these questions coming in, and we didn't have enough time. So my team, after this webinar, as a free gift, is going to do some career coaching for you in your cloud career, because we want everybody getting a job that's wonderful for them. So lots of exciting things. Leo, you want to introduce yourself before we begin?
Hi, Mike. Thank you for this opportunity. I'm really excited being here. Well, you said most of it. I am a senior manager of operations here at Go Cloud Careers. And my background, I have a bachelor in electrical engineering and a master's degree in biomedical engineering. So I've been working for more than 2 decades in the telecom area. So I have some math in my veins.
Leo's
I
being
love that. You got some math, just a little math in your veins.
Leo's being humble. He's effectively worked in networking for 20 years, and I have for 25. And Leo's incredible. So
Yeah.
let's begin and talk about it today.
All right. So before we begin, if you're familiar with us here on YouTube or in our program, we've got a lot of our students from our Cloud Architect Career Development Program, Cloud Engineer Program, and other programs here. If you're familiar, you know that I'm going to be behind the scenes making things pop up and switching screens and all kinds of stuff. So Mike and Leo will be directing me on what to do. They'll be saying, Chris, do this, Chris, do that, and I'll be making it happen. So just, we're live here. We are raw and unfiltered and unscripted. So they're going to be telling me what to do, and I'll be making it happen. So before I let Mike run off with this, and before I let Leo go practice his math a little bit, I want to tell everybody about the about our Elite Cloud Architect information session that we're going to be having this Thursday. This session will be at 6 p.m. on Thursday, and this is going to be a free information session for a brand new program that we have available for all of you. So if you desire to be a cloud architect, register and join us for this free session, so that you can learn all about this new program that we've got. And you can ask us any and all questions to make sure that this might or might not be the best program for you and your desired goals. So join us for this session. Like I said, it's completely free. We've got this new Elite Cloud Architect program that we'll be launching. The launch it will start on July 15th, but we are limiting it to only 10 registrants, only 10 people for this first round of this new program. So it's going to be extremely limited. So we want to make sure that we answer all questions that anyone might have about this in this information session. Tyrone has put the link to register over there in the chat box. Tyrone is another member of our team there in the background. So he's got that link there in the chat box. You can also find the link in the description as well. So make sure you register for that. Also, guess what? We're not just doing subnetting today. We're also going to be doing BGP next Tuesday. And if any of you joined us for our AWS workshop in April, we asked you if you wanted these things. And guess what you told us? You said you wanted these things. So we've got subnetting today. And then a week from today, we've got BGP. And now if you're in our Cloud Architect Career Development Program, guess what? You've already gotten this, but you get some more of it. So make sure you set a reminder for next Tuesday, same time, same place. Going to be everywhere. YouTube, LinkedIn, Facebook, Twitter, Twitch, whatever they're broadcasting at on Pluto, we'll be there. So join us for that as well. So that's what I wanted to share with everybody. Also, you know what? We might have a little surprise tomorrow. So make sure you're following Mike on LinkedIn. Just going to drop that there. Make sure you're following Mike on LinkedIn. Might have a surprise tomorrow. All right, Mike, back to you.
Okay, so now let's get in today's main program. We're going to discuss what is subnetting. We'll discuss what our classful address is. We'll go into depth about what goes into subnetting. We'll talk about how to subnet. And then, of course, we have to do the reverse of subnetting called supernetting, which is required for route summarization and route aggregation, which is absolutely critical for network scalability. But when we connect to the cloud providers, they only allow us to send them like 1,000 routes or 100 routes, or depending upon the cloud provider. It's usually about 100, which is nothing. I'm used to working on systems that have 800,000 routes, each coming from multiple environments. And with the cloud, we've got 100. So we're going to have to do reverse subnetting for our routing in order to make it work on the cloud, and that's called supernetting. Then we're going to get into some subnet and supernetting practice. We'll talk about subnet planning as it would pertain to your architectures, for your cloud architectures. And then we'll get into some design. It's going to be lots of fun, so please bear with us.
Yeah, Mike, Mr. Producer here.
Yes.
So apparently I did not check your framing before we started this.
Yeah, I was just thinking that. Let me bring myself out on the screen.
There we go. All right, now we got you framed up right.
Thanks for that. So what is subnetting? Subnetting is basically taking an IP network and breaking it down into small components. Server virtualization, take a server, break it down into small components. Containerization, basically take an operating system and virtualize it to make each container different than each other. Or my favorite, order a pizza, chop it up into some pieces and feed it into your friends. Because I love feeding my friends. Maybe it's the Greek person in me. We like to feed people. But, there's that. So why are we subnetting? Primarily, it's done to conserve addresses because each interface or network card needs to be on a separate network. I'll show you the implications of this in a minute. But if we didn't subnet, we'd basically be wasting millions, if not billions, of addresses on a daily basis. And we just don't have that many addresses. Chris, if you can show the slide that shows the router with 64 million IP addresses used. Okay, in this situation, we have a router. It's got 4 interfaces on it, 4 ports. It could be a server with 4 different network cards on it. And in this particular environment, we took a Class A network, which is a /8, which we'll get into in depth to explain to you what this means. Now, each one of these /8s has over 16 million possible addresses. I'm going to tell you that you're almost never going to be able to put more than 500 addresses on a subnet because it'll fall apart because all systems broadcast and scream to each other. Are you there? Hey, I'm here. ARPU has this MAC address. I have this MAC address. Apple systems are out there screaming to their buddies with bonjour, do you exist? Windows systems are sending these server message box things, all to identify each other. So we can never put more than 500 systems on a single network. So in this particular environment, we've got 16 million addresses all on a single network. And we can only go to 500. So pretty much think of it that we're wasting 16 million addresses if we didn't subnet these systems down. So that wouldn't be good. Here, with an unsubnetted network, we're basically going to use 64 million addresses completely tossed away in the trash. Chris, could you take us to the next slide where we're going to subnet it down? Now, the network architect, the network engineer, the cloud network architect decides to say, these are WAN links, meaning it's like a wire that connects 2 locations. We got a system on this side, a system on this side of the wire, totally maximum number of 2 systems that we can put there. And we properly subnetted it down. And we now only use 16 IP addresses. So I ask you, tell me in the chat box, would you rather use 16 addresses or 64 million addresses? Tell me what you think is important. And if you think it makes sense to use 16 addresses versus 64 million, give me a hashtag subnetting in the chat box of every platform that you're watching us on. Okay, wonderful. So now you know why we must subnet. Chris, if you could do me a favor and go to the next slide. Now, a long time ago, thing in the 1980s, we had something called classful addresses. Now, we're going back to the 1980s. And I worked in networking in the 90s. And even then, we were starting to subnet our networks down. And what happened is we had this is pre-subnetting days, where we had a Class A address. And when you'd look at a Class A address, it would begin with 1 or a 2 or a 3 or a 10. And the first octet, which we'll talk about later, and I will walk through it, would have like a 2.0.0.0/8. That address block, which was called the Class A, offered over 16 million addresses. And Leo's going to get good and geeky with you with the math, but the total addresses would be 2 to the 24th power minus 2. Leo's going to get into that fun math and show you the bits and bytes. It's all kinds of exciting for math people. I am not a math person, but I actually visualized the subnets in my head because I've been doing this for so long. Now, then what ultimately happened was they said, well, the Class B addresses will give you about 65,000 addresses, or 2 to the 16th power minus 2. And those addresses began at 128 all the way to 191. And they had a /16-bit subnet mask, which Leo will show you the math. It looked like a 255.255.0.0. And then we had our Class C addresses, which began from 192 all the way to 223. And they had a they were at a 24-bit subnet mask, otherwise the 255.255.255.0. And then how did Mike build his early career? I was a multicast architect, and I traveled the world working with internet service providers, TV providers, and banks on IP multicast. And that's what Class D addresses are for. And they don't get subnetted down at all. That's basically, I send to one, and anybody that wants it basically was there. And then we had this ridiculous concept called the Class E address, and that was from 240 to 255. These were for experimental research uses. And guess what? Nobody ever used them. Nobody ever used them. So I'm going to actually do the next slide, Chris, and then we're going to turn it over to Leo. I'm going to basically show what is the format of these unsubnetted addresses, and Leo's going to teach you how to subnet them, and it's going to be fun, fun, fun. So when we looked at a Class A address, where I called it a /8, basically what we had here was 8 networking bits. That's the 255. And the .0.0.0 allowed for these 16 million hosts because we had 24 bits. And when it's binary numbers, it's either on or off, 0 or 1. Now, for we Americans, we don't count 0, but the rest of the world counts 0. For example, you go to England, the first floor is a 0. And then you go to the 1. So 1 is actually the second floor. Same thing in Dubai. You go to America, we start at 1 and 2. So you may wonder how we got to 2 bits. It's because it's a 0, 1, and that's 2. So Class A, as you can see, 24 host bits, 2 to the 24th minus 2. That's the number of addresses in there. But we can't put more than 500 in a single network because of the broadcast problem. So the second we do that, poof, we got 16 million plus minus 500, and the rest of it is all wasted addresses. So then with these Class Bs, which don't exist anymore, and that's why we're on classless interdomain routing, which I'll describe real quick, we had 16 bits of networking and 16 bits of host. 65,000 addresses approximately, 2 to the 16th minus 2. We're going to get fun with math very soon. And then the Class C, it was 24 bits of networking and 24 bits of host. So, Chris, if you remove the slide for a second. So this is what we were actually talking about with subnetting, taking those blocks and chopping them down. Now, when I told you these were IP address classes that existed as Class A, Class B, Class C, Class D. So that was classful routing, which stopped mid-80s, 1980s. So if you want to know what is classless interdomain routing, otherwise known what is CIDR, it's really about taking those classful addresses and subnetting them down to smaller networks. And that's all they talk about. So if you get a CIDR range, for example, it's the entire address block. And you're going to chop that CIDR range down into different subnets. And that's what subnetting is. So now you know what is classful and classless addressing, which we talked about a little bit. What is classless interdomain routing? And now you know the point of subnetting. Take that giant pizza, chop it up, and give it to your friends. Because chances are, if it's like a 50-inch pizza or a 1.5 meter wide pizza, you're not going to eat it all yourself. Even if you tried, you're not going to be able to. And if you do, you're probably going to get a horrible tummy ache. So you're going to chop it up into pieces. Same thing would happen. I'm going to take a big IP addressing block, and then we're going to break it down. So, Leo, I'd like you to walk us through the subnetting math, and then we'll come back to me. And of course, you can ask questions of Leo and me, and we're going to do everything we can to make sure you understand subnetting. Subnetting math professor Leo Paredes, please take it from here.
Thank you, Mike. Sure. And we are talking about bits, right? Having host bits, having subnet, having network bits, host bits, subnet bits. But what are bits? Why do we need to understand bits? Bits come from the binary system. The binary system is the language the computers, the cell phones, the electronic devices, they use binary internally. They don't understand the decimal system. So when we have some IP addresses, as Mike showed, we use those numbers, that dotted decimal format, for our easy of understanding, for our readability. Behind those decimal numbers, we actually have bits from the binary system. Chris, would you please share the spreadsheet? I will now show all the basic blocks of the binary system that are the bits. So here we have 0 and 1, and I will probably need to zoom this a little bit. 0 and 1 are the only two digits that exist in the binary system. They have the same value as they have in the decimal system. 0 value is 0, and the 1-bit value is 1. And this means if I only have one digit to represent a binary number, I have two possibilities. This digit could assume the value of 0 or the value of 1. The binary system is a base 2 system, meaning it has two digits and it's based on the power of 2. So to understand the value of a binary number, we need to translate to decimal, because this is not natural for us to understand binary. For instance, if I write a binary number like 1010, well, for most of us, this doesn't really make sense because we can't think in binary. So the first thing we need to learn how to do is how to convert a binary number to the decimal system, where we can understand the value of those symbols of that number. So I will build a table here. On the first line, I will put a series of numbers starting with 0, and then 1, and then 2, and then 3, 4, 5, 6, 7. And in this number, just below it, I will put the value of 2 to the power of n. In this case, it will be 2 to the power of 0 equals 1. 2 to the power of 1 will be 2. 2 to the power of 2 equals 2 times 2, that is 4. 2 to the power of 3 is 2 times 2 times 2 equals 8. And then I keep pushing the formula to get the numbers referent that represent the decimal value of 2 to the power of the number just above it. This table represents the relative position that a bit will represent in binary. This is like in the decimal system. In the decimal system, the digit on the right represents the units. The one digit to the left represents tens, and then one more to the left represents hundreds, and then one more thousands. In binary, we don't have those names to define the position, but the relative position will be just like in decimal. Here we have the smallest digit in the binary on the right side of the number. As we move to the left, we are multiplying the value of the relative value of that position by 2. So 2 times 1. If I am in this position and I go one position to the left, I need to multiply by 4. And these are relative position values. As I told before, if I have the binary number 1010, I can just read it and make sense how much is that. So we need to convert this number that is a binary number to decimal. How do we convert this? We multiply the digit here by the relative position value. So in this case, I have 0 times 1 is 0, 1 times 2 is 2, 0 times 4 is 0, 1 times 8 is 8. After we multiply the digit by the relative value of the position this digit occupies, we will add all the results of those multiplications. In this case, the binary 1010 represents the number 10 in decimal. Of course, when we are talking about IP addresses, we are talking about groups of 8 bits. So it would be the same of having all zeros here, and the multiplication will be all zeros because I'm multiplying 0 by any value, and the sum will be the total of the multiplications will still be 10. But if I have a different binary number, let's say I have a binary number that has a 1 on this position, then 1 times the relative position value 128 will give 128. When I sum all the results, I get 138. This is how the binary system works and how we need to translate. Well, most people need to translate to decimal to make sense of this number that naturally is not understandable.
One quick point here for everybody that's in the audience. While cloud architects may not code or configure or touch the technology, we design, present, and sell it, we must have exceptional Excel skills, whether it be for return on investment models, whether it be to calculate and plan and networking. Please keep that in the back of your mind. Excel is pretty important. So you can also watch what Leo's doing here. He's not only a great professor of subnet math, but he knows Excel real well too. Go back to you, Leo.
I also want to interject here. You know, I've never actually sat in on one of Leo's math classes, but this is the first time that I've actually understood how to convert binary to like a real number. and I just got it. You did great there, Leo. That like wow. Now, as I said in the chat box, now I'm kind of scared. Who knows what Mike's going to expect from me now?
Okay, so this is our base table that we will use most of the time when doing subnetting, and we will need this table. It's very important. Now, I just showed how to convert one binary number to decimal. What if I have the decimal number and I want to convert it to binary? Let's get, for instance, the number 192. I will use the same table here, and I will write here, can divide. If I can divide this number by the relative, position on this table that has 8 positions, because here we are talking about converting the decimal representation of IP addresses into binary. So in each, the IP address is composed of 4 octets or 4 groups of 8 bits. So that's why this table has 8 positions, and we will start trying to divide by the position with the largest value or the biggest value, and then I will keep dividing. But as I build the table, you will understand. And this I will call bit. So can I divide 192 by 128? Yes, I can divide. If I can divide, if I have yes in this line, I will fix or set the bit to 1. And then 192 divided by 128, the response, the integer, is 1, but I need to get the remainder of the division. That would be 64. Can I divide 64 by 64? Yes, I can. And I set the bit to 1. And then 64 divided by 64 is 1. The remainder is 0. But I will put the formula just for the sake of building the table. Oops. This minus this gives me 0 as a reminder. But now to build the table, I will ask again, can I divide 0 by 32? No, I don't have anything else to divide, right? So I answer can divide to no, and I set the bit to 0. As I know the only value I will have here will be 0 for all 5 other positions, the answer is no for all of them, because I don't have anything else to divide, and the bit is set to 0. So this is the binary representation of the number 192 when I convert it to binary. If we multiply, again, the bits by the values of the positions, we will get just this 1 times 128 and 1 times 64. And I add everything. The rest will be just zeros, right? Because I have zeros multiplying the values will be 0. The sum of 128 plus 64 is 192. Just doing another example, let's get the number 168. And here I will be a little bit quicker. I will not use both, but I will just fix the bit here with the answer. Can I divide 168 by 128? Yes, so the bit is 1. The remainder will be 168 minus 128, 40. Can I divide 40 by 64? No, I will not get one integer. I will get a value smaller than 1, so I will put a 0 here. And I bring the 40 to the side. Can I divide 40 by 32? Yes, I will set to 1 and get the remainder, 8. Can I divide 8 by 16 and get an integer? No, I bring the 8 to the side. Can I divide 8 by 8? Yes, 1, and the remainder is 0. Can I divide 0? No, so for the other positions, I know I cannot divide. I will put zeros. So this is the binary representation of the number 168 in binary when converted to binary. We are using the binary so we can understand subnetting. That is the point here, right? There is one organization, one authority, the Internet Assigned Numbers Authority. This is a consortium of organizations that define the standards for other things, IP addresses. And this authority defined 3 ranges of IP addresses to be used inside organizations, because at some point they realized the total number of available IP addresses using 32 bits would not be enough. So they started reserving reserving IP addresses to be used inside organizations, or private IP addresses. So the public IP addresses that they can be used in the internet to connect different organizations could be enough to keep the internet working. So we have these 3 ranges of private IP addresses: the 10.0.0.0 up to 10.255.255.255, and then the 172.16.0.0 up to 172.31 192.168.255.255 and 192.168.0.0 up to 192.168.255.255. And we have here on the right the CIDR prefix or the slash prefix. The first one is a /8, the second one is /12, and the third one a /16. We will see when we are doing subnetting that this slash prefix will be really important, and we will understand a little bit more how to use this slash prefix standard when we are talking about subnetting. For now, I will show the format of one IP address. This one, 192.168.0.0, how it is represented in binary. This was no coincidence that I just converted 192 and 168 to binary here. So I will copy the binary representation of 192 to put down here, and the binary representation of 168 I will put just below the second octet here. As I mentioned before, we have 4 octets, right? 4 groups of 8 bits. So we have in the first octet 192 converted to binary. On the second octet, 168 converted to binary. And the others are just zeros, because I have 0 on the third octet and 0 on the fourth octet, right? So this is the binary representation of the IP address 192.168.0.0. We will talk about the subnet mask in a while after we go through some more content. Chris, would you please go back to the slide? And go to the next one, please. There we have a table. On the leftmost column, we have number of bits. If we have 1 bit, we can have 2 possibilities, right? This bit or this digit can assume the value of 0 or the value of 1, and then we have 2 possibilities. If we have 2 bits, we will have 2 times 2 possibilities, 4 possibilities. And this is represented in the table in the second column by 2 to the power of X number of bits. 2 to the power of 1, 2, 2 to the power of 2, 4, 2 to the power of 3, 8, and so forth. This is the total number of possibilities. When you talk about subnetting, network, and IP addresses, we will need to reserve some IP addresses. Would you please talk about this reserving IP addresses, Mike? Could you take this one?
Absolutely. So a couple things to keep in mind. When we're dealing with regular networking, we're going to lose 2 IP addresses, the 0 and the all broadcast. So let's say we've got a 192.168.1.0/24. The route, if you actually see a route on a router, it'll say 192.168.1.0/24 in the routing table. And it'll say exit this interface, for example. That's used by the router. That actually identifies the network. So we can't put an IP address on the network itself. So the first usable address will begin with 192.168.1.1. Now we also have something called the subnet directed broadcast. And what is that? If on that /24, that 192.168.1.255, I send that message, every host in that subnet is going to see it. Now, there's times where I need to do that. If I've got a VLAN and I've got basically 200 computers inside of that VLAN, and I need to see who has the MAC address for 192.168.1.67, for example, I need a broadcast. And the broadcast is going to be an ARP broadcast to find it. But Because every host responds to that broadcast and sees that broadcast, we can't address it. So in a traditional network environment, we're going to lose 2 addresses. And that's why it's 2 to the x power minus 2. We use the 0, 192.168.1.0, and we lose the all ones, 192.168.1.255. And why is it all ones? If you add up the 128 plus the 64 plus the 32 plus the 16 plus the 8 plus the 4 plus the 2 plus the 1, we get the number 255. So we can't use them. Now, on the cloud, we've got something else going on. The cloud providers typically reserve the first 4 IP addresses as well as the broadcast. So anytime we calculate subnets on the cloud, it's going to be 2 to the x minus 5, which is why, at least on AWS, the smallest subnet we can use is actually a /28. We're going to get in much more detail to that soon, but kind of keep that in the back of your mind. We're going to lose 2 in traditional networking, and we're going to lose 5 in there. And that's because, for example, if you're on the AWS cloud, they still reserve the 0 because that's networking principles for the router or the virtual router on the cloud. Then they reserve the .1 for the router, and then they keep a couple for experimental and future uses. So kind of keep that in the back of your mind. That traditional networking, 2 to the x minus 2. Cloud networking, 2 to the x minus 5. So we'll keep that in the back of your mind. I'm going to have Leo walk through a few more. And then what we're going to do is I'm going to give you a test. And then you guys are all going to answer me on the test. I'm all excited about seeing how much you've learned. And for any that you guys get wrong, we'll have Professor Leo Paredes take out his Excel spreadsheet and work on them with you one by one. And then when you guys get it, and I know you guys get it, we're going to have all kinds of fun. We're going to be doing some supernetting, which is route summarization, which is absolutely critical for dealing with the major cloud networking limitations in the cloud provider. Cloud providers networking is about 1999 grade networking. And the things that we had to do in 1999 due to lack of memory and CPU performance in their routers, we now have to do in the cloud because the way their networks are set up, we don't have a lot of flexibility. So we got to get real crisp on these fundamentals to make everything work in the cloud. So, Leo, you want to share that binary spreadsheet to make it pretty easy? I think it's on slide 12, Chris. And then have Leo walk through that. And then after that, that's where we're going to go back and we're going to do the examples. Actually, I'll walk through it and then we'll go back to the examples. Chris, share slide 11. So as Leo actually walked you through the numbers before, here you can see a /24, and he did beautifully on the Excel spreadsheet. You can see that the first octet was all ones. And if you need more explanation, we'll get Leo to get his cool spreadsheet out. The second octet is all ones. And what I mean by the first octet is the stuff that you see in the top. The first 8 ones. The second octet is the second series of ones divided by the period. The third octet is the series of ones. And the last octet is all zeros. That's a /24. Now that'll give us roughly 254 addresses. 2 to the x, 2 to the 8th minus 2. Now let's say we want to chop that subnet in half. No big deal. Now you can see what we did in the next line. One line down, where you can see the all ones in the first octet, the all ones in the second octet, the all ones in the third octet, and just a 1 and then all zeros. Now we have 2 to the 7th minus 2 in terms of IP addresses. And guess what? That gives us a total of 2 to the 7th, and then minus 2. Now you can see we further subdivide this class C address. 1.1. All the ones in the first octet, the ones in the second octet, the ones in the third octet, and then we get to that 4th octet, we've got a 1.1. Now it's a /26. Now, I'll give you another secret Mike's I hate math method for determining the available host on a subnet. Let's come down to the next line where it's where you can see It's 255.255.254, right? And you note that that's actually represented by all ones in the first octet, all ones in the second octet, all ones in the third octet, and 3 ones in the fourth. Mike's I hate math secret is 256 minus your subnet mask minus 2 will also tell you the number of hosts. And why does that work? Well, 2 to the 8th gets you 256, right, Leo? And then if we subtract 2, we still get to the same point. So you can either do the math, and it's pretty easy on a scientific calculator, 2 exponent whatever number minus 2, and you'll get your results. Or if you don't know, and you just want to do quick addition, subtraction in your head, 256 minus your subnet mask in numerical terms, 224, and poof, you get your answer. It's 32 minus 2, which gives you 30. So any way you want to do the math works for me. Leo taught you the correct way, and I suggest you use it. But you find yourself in a pinch. You're in a customer meeting, and there's like 800 people in the room. 256 minus this, you can do it in your head. I think my cat Cindy can do it in her head, but my cat Cindy is exceptionally smart. And poof, you got your number. So kind of keep that in the back of your mind. So what we're going to do at this point is we're going to do a quiz. And when we get to the quiz, Leo's going to demonstrate the first 2 with you. Then I'm going to quiz you. And if you don't get it, Leo will walk through each answer. So here's what we need from you guys. Lots of paying attention. And when I ask you guys a question, we're going to ask you to pop it in the chat box or your LinkedIn or on Twitter as a comment, because we want to know you guys are getting it, and knowing that you get it is important. And then if you guys get it, woohoo, we're thrilled. If you guys don't get it, Professor Leo with his math skills and his cool Excel spreadsheets is going to walk us through it. So Leo, so Chris, why don't you bring us to the subnet problem slide, and then from there, Leo will take over for a few minutes, and then we'll do it together. Actually, I believe it would be slide 14.
Yes, the first example is, or challenge for you, is 192.168.1.132/25. Let's. Okay. We will do the quiz first, or show the math first, Mike?
Why don't you walk them through the first one, and then after that, we'll quiz them on the next one. Then I'm sure you're going to have to demonstrate the second one. And from there, we're going to go into quizzes.
Sure thing. Chris, would you please open the spreadsheet? And I will zoom a little bit here. Yes, even. Here is the first example, 192.168.1.132/25. What does the /25 means? It means that we will need to fix the bits that represent the network or subnet bits. Well, I showed before that this 192.168 is a /16, is originally a /16 network. So I marked 16 bits as N for network bits. And to get a /25 subnet, I marked other 9 bits with an S to mean subnet bits. So in total, I marked with N's and S's 25 bits. And these bits I will set to 1, because for all IP addresses inside this subnet, these 25 bits must be the same. This is the /25. This what is the mean of the /25. 25 bits of the original IP address for this subnet must be fixed. The other 7 bits are marked with an H as host bits, and these are the bits that the network engineer or the professional responsible to assign IP addresses to the servers, printers, notebooks, devices on the network, they will use these bits, setting them to ones and zeros to define the IP addresses. So /25 means I need to mark 25 bits as one to get my network mask or the subnet mask. And then after I have those bits set to 1 for the bits that are fixed and 0 for the bits that can be used as host bits, I translate this number to decimal. So I have 8 ones here. This is the max I can have with one octet when I convert to decimal is 255. This other is also 8 ones. One more, 8 ones. And here I have one on this position that is when we remember the table, that bit represents this is occupying this position, so it has the largest value. So I have 128, the value here, and all zeros, so this is 128. So the /25 mask in dotted decimal will be a 255.255.255.128 mask. When we are talking about getting to know the subnet, we want to know how many IP addresses are available. We want to know what is the first IP address that in that subnet mask, and what or which is the last IP address in this subnet. So I will use another table here. And this is getting the original IP address 192.168.1.132, and I will convert these decimal numbers to binary. I already have formulas here. I will get this binary number. And then to find the first IP address in this subnet, before, when creating the subnet, I fixed or I set these 25 bits as 1. So to find the first IP address, I need to keep those 25 bits as they are from the original IP address. And then I have the 7 host bits. To find the first IP address, I will set all of them to 0. This means I will get, since 25 bits are fixed, these 3 octets are still the same, right? 192.168.1. Now, in the 4th octet, this bit is fixed in the subnet mask, so I need to keep the same bit as it is, and I will set the 7 host bits to 0. So this is the first IP address in the subnet, 192.168.1.128. And the last IP address, I will still keep the 25 bits as they are originally converted from the IP address informed, but the host bits now, I will set them all to 1. And then the last IP address is 192.168.1.255. And the total possible number of IP addresses in this /25 subnet, I will get by using 2 to the power of the number of host bits. 2 to the power of 7, I get 128 total possible IP addresses, remembering that we need to reserve, thinking on the data center, we need to reserve 2. So the total number of usable IP addresses for this subnet is 126. Well, this is how we get the first IP address, the last IP address, and the number of total or usable IP addresses in one subnet using the subnet mask informed. Back to you, Mike.
Excellent, Leo. Thank you so much for that. So we're going to do the next one. I hope you guys can all do it on your own. I'm going to actually talk about the address, and then I'm going to put it in the chat box in YouTube. And then from there, I'd like you all to calculate the beginning of the subnet, meaning the 0 address, the broadcast address, which is the all ones, and then from there, tell us what are the usable addresses, give us a range. The IP address that we're going to talk about is 192.168.1.17/28. So I'll type it in the chat box. I'll say it again in case you're on LinkedIn or someplace. 192.168.1.17/28. And if you calculate the subnet right, you're going to know what is the beginning of the subnet. So why don't we do this? Why don't you all first tell me what is the beginning of the subnet? And then after that, I'll ask you what is the end. But let's do one thing at a time so we don't go crazy in the chat box, because it'll be hard for us to tell. So please tell us, where does this subnet begin? What is the address used by the router, the network address? We could play some Jeopardy music. Do 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 bump 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 bump. Come on, give me some answers in the chat box. Can't wait to see what you guys come up with. Where does the subnet begin? You know, it may take a little bit because there's a little bit of a delay from the time we speak till the time it shows up on all these various platforms, but I'm looking forward to your answers. Well, I think it would work better with a little Bob Marley, Ziggy Marley, Damian Marley, and Skip Marley music in the background, but that's my personal preference. Well, okay, I'm seeing one person who's typing in the chat box. Let's get some more answers from you guys. Okay, I'll give you a few seconds, then I'll actually answer it for you. And then after that, we'll have Leo walk you through, since I think we need to get some more people. So the subnet's going to begin at 192.168.1.16. It's going to end at 192.168.1.31, which means .17 through .30 are going to be usable addresses on the subnet in a traditional environment. Now, if we were on the cloud, we'd lose 5, but let's do traditional networking before we do the cloud first. So, Leo, maybe it's worth you actually walking everyone through this example.
Sure, Mike. Chris, would you please share the spreadsheet? And here we have, I reduced this to reduce the noise. So the first thing is to find the binary subnet mask, right? We have a /28, so we need to fix 28 bits for the subnet. So I have set all 28 bits as 1, and then the remaining bits are host bits. When I convert the original IP address informed 192.168.1.17, and I convert it to binary, and I mark here all the bits that I need to keep fixed. I have this, well, converting to binary, I have this, and the /28 means I need to keep all these 28 bits from the original IP address. I need to keep them fixed when I'm trying to find the first and last IP addresses. Having these bits, I will copy them down here just to make sure I don't mess with the formulas up there. So I have the binary number here, and I have the remaining host bits that I can fix. I can set all to 0 to find the first IP address in this subnet. So the first IP address converting to decimal is 192.168.1.16. When I copy this same bit that must be fixed, I cannot touch these bits inside this subnet. I can only play with the host bits, and to find the last IP address, we'll set all host bits to 1, and the last IP address, that is the broadcast, will be 192.168.1.31. So the basic or the main aspect of finding those numbers is fixing or defining how many bits and which bits you need to keep as they are from the original IP address, and then playing with the remaining host bits. So those are the first and last IP addresses, and the number of host bits remaining after I have a /28 subnet is 4 bits, 2 to the power of 4, 16 total IP addresses, 14 usable IP addresses. Back to you, Mike.
Leo showed you the correct way of doing this, and I want all of you to get it. But I'm going to give you a little cheat math real quick to try and help you a lot. So a /28 is 240, and it's a 240 because it's a 1 in the 128 place, a 1 in the 64 place, a 1 in the 32 place, and a 1 in 16 place. So 128 plus 64 equals 192 plus 32 equals 224 plus 16 equals 240. So when we know that, that gives us something. So if we backed into it by taking 256 minus 240, we get the number 16, right? So we know 16 minus 2 is the available addresses. So then if we look at what's divisible by 16, 17 is divisible by 16, right? By a little more than 1. And because it's greater than 1, the subnet can't start at 0. It has to start at the thing that it's greater than 7. So it begins at 16. So I could tell you by doing simple math, which is just basically doing the same thing Leo did in a way that makes more sense to my brain, that 256 minus 240 gives me 16. So my first subnet on a /28 will begin at 0 and it'll end at 15. The next subnet will begin at 16 and it'll end in 31. The next subnet will end at 30, will begin at 32 and end at 32 plus 16, 47. The next one will end at 48 and end at 63. The next one will begin at 64, for example. So let's try this. Let's get rid of the spreadsheet. And then let's give you, I'm going to give you another simple one off of the same formula Leo showed you and I showed you before we get into anything more complicated. So I'm going to put this actual address over here, and it's going to be a 192.168.1.33/28. So where does this subnet begin? Remember, 256 minus the mask, which is 240, gives us 16. So It has to be divisible by a number. If it was 13, it's not divisible by 16, so it would begin at 0. If it's 18, it's divisible by 16 with 1 and a remainder, and it would be there. If it was 49, it would be divisible by 3, so it would begin with 16 times 3, which is 48. Okay, good job, Carl. The subnet begins at .32, and it ends in .47. So Leo and I basically showed you 2 ways. Leo showed you the proper math, which I want everybody to learn. And I showed you the cheat math that we network engineers and network architects do when we're speaking at a networking conference. And out of nowhere, there's a heckler in the group that wants to know where the subnet begins, because they have to ask the network architect with 20-some years experience, hey, where's your subnets begin? Because they think it's going to be fun. And it happens all the time. So keep that in the back of your mind. So at this point, we'll give you another one on this range, and then we're going to go into a new problem. Please tell me where this absolute subnet begins. 192.168.1.72/28. We're going to stay on this same /240 just to make the math a little easy. Where does this subnet begin? Where does it end? Okay, Kyron, great job. Auntie, great job. Parth, almost there. Just off by a couple of numbers there, but you're getting there. So let's do this. I'm going to show you my cheat way. Then we're going to have Leo go back to it one more time. And I think we're going to be in some really great shape. I'm actually going to share a spreadsheet at this point. And it's not going to be a pretty spreadsheet like Leo's. It's going to be a mic equivalent of a spreadsheet. Chris, let me know when you share my spreadsheet. Okay, so in this particular situation, the number I gave you began with 72, right? So here's the way I like to look at it. 128, 64, 32, 16.
Can you zoom in some, Mike?
Yeah, I think I can do that. 8, 4, 2, 1. If I count 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. So now maybe I'll just shrink this down a little bit so you can see the whole thing. So the number that I gave you was a 72. But I also gave you a /28, which is 4 bits of subnet mask. So if we actually calculate a /28, it's going to be 1 over here, 1 over here, 1 over here, and 1 over here, which 128 plus 62 plus 32 plus 16 is going to happen to equal the number 240. So that's what we're dealing with, is the number 240. So if we use Mike's cheat math, which is 256 minus 240, so we'll go over in here and we'll make this equal 256 minus 240. And I know I could have used really good spreadsheet template formula, but I wanted to make it real simple for you guys. Note the answer we get is 16. And the reason I stopped at 16 was we have 4 bits of subnet mask because it was a /28. So I knew they were all ones and to zero this out. So now the number I gave you was 72. 72 divided by 16 gives us what? 4 and change, right? But let's prove the math. Let's take 72 over here. Let's do 16 over here. So let's do over here, let's do an equal 17 divided by 16, and we get 1.06. So, no, that can't be right. Oh, 72 divided by 16. I know I did something funny over there. So 72 divided by 16 gives us 4. When it comes to subnets, there's no in between. There's either a 3, there's a 4, there's a 5, a 6, a 7, what have you. So now let's do this. Let's take the number that I gave you, which was 72, divide by 16, which gives us 4. So what is 4 times 16? 64. Okay, that's the beginning of the subnet. Now, if we add 16 to this, we're done. But remember, counting the 64 counts as 1. So that actually counts as the first number. So if we add 15 more, at least in American terms, or a total of 16 terms, 16 if we count the 16 as a 0, and we add 15, that gives us the end of the subnet, which is 79. So that's why our range is 64 to 79 with usable addresses of 65 all the way to 78. Now, that's the way I do this funky math in my head. I absolutely detest math. And I do these things on the fly. And the reason I do it on the fly is I'm constantly looking at systems and I need to be able to do it. Now, I'm going to stop sharing mine and I'm going to have Leo share with you the correct way to do it. Both of us will get to the same place. I'm just trying to show you if you find the one way a little complicated with the math, Mike's little addition, subtraction, cheat sheet way to do it might also be helpful for you as well. So let's try this. I want to make sure by the end of the day and all the examples you guys get all this before we move on to the supernetting, which is equally important. Leo, back to you.
Sure, Mike. If you please share the spreadsheet, Chris. Here we have the same 28 bits set to 1 in the subnet mask. And these 4 here are the bits Mike showed on the positions 128, 64, 32, and 16, adding up to the decimal 240. So we need to keep all these 28 bits fixed as we convert the original IP address 192.168.1.72. We get this binary number, and we need to keep 28 bits fixed. And I will copy to avoid messing with the formulas. And then we set the remaining host bits to 0 to find the first IP address in this subnet, that is 192.168.1.64. And then I will copy the same 28 bits from the original IP address and set all host bits to 1 to find the broadcast IP, that is 192.168.1.79, meaning the last usable IP address is 192.168.1.78. So the process is the same. You mark the bits you need to keep fixed because they can't change inside the same subnet, and you set to 0 the host bits to find the first IP address, and you set the host bits to 1 to find the broadcast IP, that is the last IP address in that subnet. Back to you, Mike.
Okay, so now we showed you 2 ways to do this. So now we're going to go to another problem, and this is going to be real simple. It's going to be a very different subnet, and the subnet we're going to give you is, and the address we're going to give you is going to be 10.0 0.0.2. It's going to be a /30. Now, what I'm also going to do when I give you this is I'm also going to give it to you. And that's the /30 is CIDR notation. I'm going to give you the subnet mask in decimal notation as well, which is going to be 255.255.255.252. So whether you use Mike math or Leo math, I'd like you to tell me, where does this subnet begin? 10.0.0.2/30. Okay. Subnet begins at .0. The range is 0 to 3. So far, I'm getting some great results. And, it dawned on me that I called the CIDR notation out of the blue, perhaps. When we see the slash with the number of bits, that's CIDR notation. When we use the 255.255.255 to something else, that's actual decimal notation. Either one is totally fine. But I'm liking this. Emmanuel got it. Auntie got it. Carol got it. Kyron got it. Ray, good job on the second time. I'm going to assume it's a typo. Good job. I see. So some of you guys are getting it. So while we're at it, let's stick with this easy subnet. I'm going to give it to you in both CIDR notation, meaning that slash number, and decimal notation. So now what if I told you, and I'll pop it back in the chat box, if we do 10.0.0.9/30, otherwise known as 255.255.255.252. Where does that subnet begin? What's the range of addresses from the 0 to the broadcast? Okay, I'm starting to see some answers here. I'm feeling really good about this. We're going to go through more examples. We're going to stick on this basic one before we get into much deeper ones. Now, for those of you that got it correct, and I'm watching all these correct answers pop in, did you use Leo's super smart math, which is the correct way I'd like you to learn it, or did you use Mike's cheat math? I actually go back and forth and use both. You can tell me that in the chat box as well. Steve used Mike's cheat math, and that's fine. Steve's a martial artist like me and thinks a lot like me, so I would expect him to use similar ways. We also posted a poll there. Karen, good job using Leo's math. I'm really happy. Ray used mine. It's fine. Emmanuel went back and forth. That's the optimal way. That's what I do myself. So I'm going to give you another one in this similar size subnet in here. And then from there, what we're going to do is we're going to have some fun, and we're going to use a different subnet. We're going to make sure all you guys and girls are crisp on this. And then we're going to get into supernetting, which is like my absolute favorite thing, because that's how we make networks scale. So while we're at it, let's go back. And now I'm going to give you another thing in that 10.x address space. I'm going to give you a 10.0.0.0.62. And that's going to be a /30-bit subnet mask. 10.0.0.62/30. The mask will be 255.255.255.252. Please tell me the range over there, meaning where the subnet begins and the broadcast, just like you guys and girls did last time. You did a great job on the last one. Show me where it begins and where it ends. Good job, Auntie. It begins at a 60. That's the network address, and the broadcast is 63. Ritika, Maxi, good. Well, Maxi, almost. AJ, the 61 is the first usable address completely. The 60 is the beginning. So you gave me the first address, which is usable. Emmanuel, all good job. Steve C, 60 to 63. Excellent. And since we know that 256 minus 252 is 4, right? We can just see what's divisible by 4, and then we'll be in good shape. But that's a good way to check your math on there along the fly. Steve, you got it. With the 252, the first one begins at 0 and ends at 3. The next one begins at 4 and ends at 7. The next one begins at 8 and ends at 11. The next one begins at 12 and ends at 15. The next one begins at 16 and ends at 19. The next one begins at 20 and ends at 23. The next one goes 24 all the way to 27, and so on and so forth. You guys did great. Okay, so we're going to go to a new subnet now. But I'm going to give it to you in that CIDR notation with the slash, and I'm going to give you the decimal notation. Something tells me if I give it to you in decimal notation, it's going to be a lot easier for you. So with this particular subnet, which I'm going to pop into the chat box right now, and I'll also mention it for the folks in case they're on LinkedIn or Twitter or somewhere in between. So in this particular case, the address we're dealing with is 172.16.1.27/27. Now that means 255.255.255.240. And I typed it wrong in the chat box. So let me actually correct my actual spelling errors. 172.16.1.27/27, otherwise known as 255.255.255.224. Now that I typed it correctly into the chat box, where do we think this subnet begins and it ends? Where's that range? Look at that. You guys figured out it begins at a 0. Wait. Yes, it begins at 0. And it ends at 31. Good job. So we'll do one more with this kind of subnet mask to make sure you guys get it. And then we'll move on to the next one. We'll do a 172.16.1.66/27, which will have a mask of 255.255.255.224. Where does it begin and end? What's that range? Okay, good job. For those of you that did the math correctly, it begins at dot 64 plus 31. What's 64 plus 31? Should be 95. That's the range. Now more of you guys are coming in and start typing in stuff in the chat box. Good. Now I'm starting to feel better, like you guys are going to get it. I'm getting it. And I type stuff funny all the time. And it's okay if you try and get it wrong as long as you're learning, but keep trying. When we don't take a shot, we always fail. You miss 100% of the shots you don't try. When we try and fail, we can still learn and be better next time. But if we don't try, we never advance. So you guys are doing great. Give yourself some credit. This is not the easiest thing in the world. If it was, we wouldn't be doing a webinar on it. You guys would all just read a 4-word LinkedIn post or a 60-second YouTube short and know it. That's why we're working on it. That's why these skills are valuable, because you have to fight a little bit to get them. So you guys are doing great. I'll give you one more. This one's going to be relatively easy, but, you know, when we do the math, 10.0.0.9/24, otherwise known as 255.255.255.0. What's the range of addresses here? Starting with what is the router address? What is that broadcast address? If you guys want, I can bring in Cindy photos in the short term, give you a little relaxation, look at some photos of my cat having a good time. She only brought me 2 lizards this morning. It's been a slow day because it's been pretty rainy. Goes outside, brings in a lizard in her mouth, lets it go, runs around the house and rechases it, then brings it to me and then lets it go and rechases it. It's kind of hilarious. Okay, you guys are doing great. You guys realize that it begins at 0 and ends at 255. Now, I'm proud of you all. Keep trying. You guys are doing good. And Kingsley, yes, the first usable address is a .1, but I wanted to know where the router started. So still good job, Kingsley. Santa Bar, Richard, I'm not really sure where you're beginning with the 4, but I know you real well and you're a super impressive guy. You'll figure it out. Cybersecurity, good job. Barrera, good, but the subnet ends at 255, not 254, but close enough. 255 is that directed broadcast. Who has the MAC address of this? Or a response where I want to get everybody to respond. Why 0? Okay, so Richard, the 0 is not a usable address. It's what's going to be on the router. So the 0, when it's all zeros that Leo showed you, actually explains the subnet to the routers. And the 255 is the broadcast. So the usable addresses are .1 to 254, but 0 is the network address. So great job. Okay, I think we're getting somewhere. Now I'm going to give you another one, and then we're going to end on the tricky one. So in this particular case, I'm going to give you a 172.17.3.9/29, which is going to be 255.255.255.248. Where does this one begin? Where is this one end? What's the range here we've got? Give you guys some time. Good job. Good job. Now I'm starting to see some responses. I'm getting excited. I'm happy. I feel like you guys are all getting it. I'm going to give you another one in this sort of place. 172.17.3.19. 172.17.3.19 /29 255.255.255.248. Where does it begin? Where does it end? Okay. You guys are getting it. You're giving me the range. Beginning begins with a .16. It's a .248. So what is that? You could either use the fact that we've got 3 host bits. 2 to the third minus 2 gives us usable addresses, but 2 to the third gives us the address. That means 248 works perfectly. Mike's cheat math. 256 minus 248 also gives us a total of 8. Either way you got there, I don't really care how you got there, as long as you can see it. I see subnets in my head. I can literally see when I'm designing a network that has 100,000 different subnets in it, where there actually are, and I can visualize the traffic going from point A to point B. That's me. My brain works a little differently. Most people need Leo's math, which is the right way to do it. So any way you want to do it, I don't really care how you get it, as long as you get to the results. But I want you to understand the Professor Paredes math, because that's the correct way to do the math. And when you understand it at that level of depth, it becomes really easy. Once you've learned it that way and you truly understand it, you can just see it in your head like I do. But, that takes some time. And before you can just visualize subnets for a bank and every single subnet they've got in their 2,000 locations or 5,000 or 10,000 locations, you got to understand it first. So IP addressing is wrong. The whole architecture falls apart. And we're going to show you why in a few minutes. So now we're going to do a new one. And then we're going to end on the tricky one, which if the only people that get that one are Benedict and Mark before I explain it, I totally understand that, and that's okay too. But that one's kind of the tricky one. So we're going to save that one for last. The next one we're going to do is going to be a 10.1.1.1/30. /30 is 255.255.255.252. Where does this subnet begin? Where does it end? And Mark, please stick around for the next one, because that host route might trick a few people. Might not. Oh, nice. You guys are doing fantastic. Derek, good job. Kyron, good job. Cybersecurity, nice. Maxie over there in France, great. Kingsley over there. I don't know where you're at, but it's a Nigerian name, so I have a theory there where you're at. Sanabar, not sure where you're at. Ray, fantastic. Vajasana, fantastic. Garl, great job. Auntie. Okay, I'm loving this, bro. Abazim, great job. Barrera, and if I mispronounced anyone's name, I am sorry. I'm loving this. You guys are doing fantastic. Okay, before we go into the exact opposite, which is supernetting, which is super critical for cloud computing, I'm going to give you another one. Now, this is going to be a bit on the tricky side. So I want to see if you guys get it. Now, this is going to be the subnet mask. Now, if you just remember, if you can't do the math, don't worry. You can just remember this for your head. And the address we're dealing with right now is 172.16.1.27/32, otherwise known as 255.255.255.255. Where does that subnet begin and end? And I think you guys could probably do it. But if for some reason you can, I'll just explain this specific use case to you and you're never going to have to calculate it. Nice job. Real one, good job. Auntie, great job. Jasana, good job. Kyron, good job. Sanabar, good job. Derek, good job. Abazim, Rika, excellent. This is what's called a host root. It only allows a single address in that subnet. So it's just .27. So if you see a 10.1.1.1/32, the only subnet that's allowed is 10.1.1.1. It's called a host root. Now, where do we use a ridiculous /32 subnet? Because you can't put a host and a router on that same subnet, and because you need more than one address. So this is what's used for a router identifier, otherwise known as a loopback address in most cases. And we use it because we put a logical address on a router. So let's say we've got an Ethernet port on a router, and it's one router plugged into another router with a crossover cable. If the wire goes down, the whole subnet goes down. Now, if you wanted to SSH into your router, and you were going to do it on the Ethernet's IP address, say 10.1.2.2/30, and this address went down, you could no longer secure shell into the router and you'd lose connectivity to the router. So if a router has two connections, we create a logical address on the router called a loopback address, and we use that as a router identifier. Routing protocols like BGP need a router identifier. Routing protocols like OSPF need a router identifier, so we use it as a router identifier. And we also use it as a means to make sure that we've got an interface that cannot go down under any circumstances. So that's what that special /32 is. Now you can keep it and remember it. Okay, so at this point, we talked about subnetting, taking one large network and chopping it down into little mini pieces. I don't really eat grains, but I've got a lot of friends that always want to eat pizza. So I ordered a pizza and I chop it up for them, and that way everybody's happy. My friends would not be happy if I said, here, you chew this piece of the pizza, you chew this part of the pizza, and everybody shares the pizza and they meet in the middle. That'd be a germy environment, not so great. So keep that in the back of your mind. We do these things, and that's why we do these things. So we're going to go into supernetting. Now, what is supernetting? It's the exact opposite. So instead of chopping things down, we bring them up. Why on earth would we chop? We take two small supernets and bring them into one, or two subnets and bring them into one. Well, maybe, just maybe, somebody decided to use like a /28 for a LAN, an Ethernet segment. I'm going to give you a secret. If you're using private addresses, use a /24 in most use cases for an Ethernet segment, because that'll give you upwards of 254 servers. Now, you may think you only need 10, which is what most people do. And they try to be good stewards of IP addresses by not wasting them. Here's the thing. Give yourself capacity. You think you need 2 servers. The next thing you realize you need 2,000. But we can't put more than 500 in the subnet. So that could be one reason. Although the reality is we could just create another VLAN or another subnet and route between them. Now, the next time we have to think about this, and this is really important, is with regards to routes. In the traditional network and data center, you can think of that as a Ferrari in terms of super speed. We can do whatever we want. We can have as many routes as we want. But in the cloud, we can send them 100 routes. So if you've got 5,000 routes in your data center's routers, and we need to make the cloud be able to reach all your environments, we can't send them 5,000 routes. We can only send them 100. So what we can do is we can take the 5,000 routes and summarize them into maybe 2 if we did our IP addressing correctly, and then share those 2 routes with the cloud provider, and then we've got 98 left over. So that's the point of supernetting. Supernetting is the exact opposite of subnetting. So I'm going to have Leo walk you through taking 2 subnets and combine them together, just to show you the academic math behind it, because I want you to all understand the math. Sometimes it's fun to geek it out and really get to the underlying math, and other times, it's more fun to take it at a higher level. So Leo is going to walk you through this example. Leo is going to bring out his cool spreadsheet, and he's going to take the 192.168.0.0 subnet /24 and the 192.168.1.0 subnet /24, and he's going to make a big subnet out of the 2 little subnets. And after that, we're going to have a little more fun with this. We'll go through some examples, and then I'll talk about IP address planning as it pertains to cloud architectures and network architectures. What's going to fall apart, which I'm going to show you, which is what we network architects see 90% of the time. People didn't understand this. They designed their IP addressing wrong, and here's what happens. Their cloud architecture falls apart. Their network architecture falls apart. Their multi-cloud architecture falls apart, and we've got a disaster. And then people are called into the chief information officer's office, and it's not a good situation. You don't want to be there. So Leo is going to walk you through the 192.168.0.0 subnet and the 192.168.1.0 subnet /24. Let me hand it over to you, Leo.
Sure, Mike. Chris, please share the spreadsheet, and I will demonstrate using the same tables we had before. I had here the 192.168.0.0/24 subnet with 24 bits set to 1, meaning from the original IP address, after I convert it to binary, I will need to keep 24 bits as they are. I am just demonstrating the first and the last IP address just to emphasize that the same subnet bits remain from the first up to the last IP address in this subnet. In the other subnet, 192.168.1.0/24, I also have 24 bits set to 1, given the decimal or the binary subnet mask. And I have converted the 192.168.1.0 to binary, and I highlighted the 24 bits that must remain the same for all IP addresses in this subnet from the first up to the last. 0/24. I also now, what is common in these 2 subnets regarding these 24 bits that are fixed? I noticed that only the bit 24 changed from this subnet to this subnet. If this bit is changing, is the only part of the subnet that is changing, I can call or name this bit 24 a virtual host bit, meaning I will uncheck it as a subnet bit. And then I have 23 bits that are common in both subnets that remain the same. This means I can get this subnet with these 23 bits that are fixed, and then I can find the first IP address for this new supernet in this case, because I called the bit 24 a virtual host bit, but pardon, I need to emphasize I'm not actually changing anything in those subnets, right? The IP addresses are assigned, the ranges of IP addresses, they remain the same. But I'm only doing this to advertise less IP addresses to another router, another network. So having the 23 bits fixed, I change all the host bits, including my virtual host bit, to 0 to find the first IP address. And I do the same. I change all the host bits, including the virtual host bit, to 1 to find the last IP address. And then I can say that both subnets above 192.168.0.0 and 192.168.1.0 that are both /24 subnets, they can be supernetted in a 192.168.0.0/23 supernet. Back to you, Mike. You are muted, Mike.
Thank you for that, Leo. We can remove the spreadsheet now, Chris. So what you see that Leo did is he took two subnets that were right next to each other and combined them. So this is why I wanted you to learn the subnet math the Leo way. Because now to turn Leo's math into Mike's math, we got to get a little funny. So I'm going to pop this into the chat box. The subnet that we're talking about is going to be a /23, which is a 255.255.254.0. So as you will recall, it's 2 to the x minus 2 and 2 to the x to get to the total. So normally in that last octet, if we have 255.255.255.0, we have 256 because that's 2 to the 8th. But now we're moving over 1. So it's going to double. And that's going to bring us to 512. Of course, minus 2 because we lose the first one and we'll lose the last one. So that's how we're getting a /23. So Chris, why don't you do this? Share, because I'm going to work on the slide with everybody. Share slide 15 where it says Supernet project. And I'm going to actually walk through this and try and show you the easy Mike's math equivalent of this. So Leo took 192.168.0.0 and 1.0 and made it a /23. I'm going to do the same thing. I'm going to take the 192.168.2.0 and the 192.168.3.0. And we're going to combine them. So if we combine two /24 subnets, we've got to move the number over 1. So what subnet mask is it going to take to combine 192.168.2.0 and 3.0? Is it going to be another /23? If you agree with me that it's going to be a /23, work with me and tell me that in the chat box. There's a reason we're doing this. Okay, Steve sees it. Auntie, it's going to be a /23 to combine 2 and 3. It's going to be a /23 to do 192.168.2.0 and 3.0, just like it was a /23 to combine 192.168.0.0 and 1.0. Okay, now, if we combine 192.168.0.0 and 1.0 into a /23, and then we could take the 2.0 and 3.0 and combine that into a /23. What if we wanted to combine all 4 into a single address? Well, we take two 24s that are next to each other, combine them into a /23. And if we want to take two /23s and combine them together, we got to lose another bit. So it becomes a /22. So you could do it in one of 2 ways. You could just look at this and see 192.168.0.0, 192.168.1.0, 192.168.2.0, And 192.168.3.0 all /24s all turned into a /22. Or you could take the 2/24s and turn them into 2/23s and then convert that into a /22. Does that make sense to everybody? Let me know in the chat box. Okay, good. Okay, now everybody, since you guys look like you're getting it, I'm feeling pretty good with you guys. Now I want you to take the second block, the 10.0.0.0/24, the 10.0.1.0, the 10.0.2.0, and the 10.0.3.0, and give me one single subnet that's got all four of them. And right after this, we're going to get into the cloud architecture and network architecture piece of why this is so critical. So combine these second set of things in the slide, the 10.0.0.0, 10.0.1.0, the 10.0.2.0, and the 10.0.3.0. And tell me what one single supernet that's going to combine to. Pop it in the chat box when you're ready. Rika, you're great. It will be a /22, but give me the actual subnet or supernet. Where does it begin? That's where the /22 begins. But you are correct. It is a /22, Rika. So is this the subnet, everyone? .0.0.0/22? Which I think it's just a typo you made, but I'm going to assume you're correct there. Nobody makes more typos than I do. With my hands that have done 20 plus years of martial arts and have all kinds of arthritis that I'm from. Silly living. Okay, so just for fun, if we have a 10.0.0.0 and a 10.0.1.0, can we combine that to a /23, everybody? And then can we take a 10.0.2.0 and a 10.0.3.0 and turn that into a /23, just like we did last time? And can we then take a /23 and a /23, borrow a bit, and convert that into a /22? Okay, so we're going to do one more of these examples, and then we're going to talk about the cloud architectural implications of this, the network architecture implications of this, because there's a point there's a reason we're doing this network skills training and networking for cloud computing. Because networking and cloud computing are really one of the same things. Okay, so now, last one. We have the last block over here, 10.1.0.0, 10.1.1.0, 10.1.2.0, and 10.1.3.0. Where does this network begin? Where does it end if we summarize it? You guys know the math. I'm watching you calculate it over there in the chat box in your heads. I could feel it, the knowledge that you guys have in your heads. So show me in the chat box. Okay, Steve, you said where it starts is easy. Give me that one as a start. And you're right, where it starts is easy. And if you realize this isn't much different than the last time or the previous example, other than which things are in play in the first 2 octets, which aren't in play at all, really. It all comes down to the last 2 octets for this. Okay, Ritika, well, you gave us the first /23. Actually, no, you did give us a /22, but you missed one of the subnets. But you're almost there. You missed the .3, Ritika. And yes, it would be a /22 that you would give us, which is typically correct. And if, okay, exactly, Ritika, yes. So if you look at 10.1.0.0 plus 10.1.1.0 plus 10.1.2.0 plus 10.1.3.0, they all can combine to 10.1.0.0/22. And therefore, the range is going to be 10.1.0.0 all the way to 10.1.3.255. Okay, Chris, you can bring me back on the screen. Get rid of the slides. We've got a couple more slides after this, after we regroup and talk. So why are we doing this supernetting thing? In networking, we do it for a couple of reasons. In networking, I want you to imagine a router that's got 10,000 routes on it. And every time something changes in the router, the whole routing table has to recalculate. Somebody reboots a subnet with one PC in it. Poof, router reboots. Router gets another, the routing protocol has to deal with an IP subnet going in, which causes all the routers to recalculate the routes. Now 2 new subnets come in. Poof, all the routers got to recalculate the routes. 3 subnets get lost, they go down. Routers have to recalculate the routes. At some point, what you get involved is a database in these routers gets so big with all these routes coming in and coming out and coming in and coming out that they have to recalculate every single time stuff goes up and stuff goes down. Now, imagine you had to do math nonstop in your head. Calculate this, calculate this, calculate this, calculate this, calculate this. I can tell you personally, I'm going to get a math headache. I don't like doing math. But, you know, whether you're running on a treadmill at 15 miles an hour, at some point you're going to get out of breath and you're going to fall unless you stop it. Well, that's really what goes on with the routers. They basically get overloaded with too many routes, and then the CPUs turn into 100% because they get too busy calculating routes, and then the router crashes, and then all your network falls apart. So here's the thing. The network falls apart. The servers that are now using the network can't reach the network because the network doesn't exist. The users who are using the network trying to get to the servers on the network got nothing because the network doesn't exist. So now you get a total outage, and it's all related to too many routes on the routers. And that's why we've got to summarize routes, because we want to reduce the workload on the routers. Now imagine you're AWS, and let's say you've got 1 million customers, and each customer wants to give you 20,000 routes. Do the math. 20,000 routes, 1 million customers. Now start thinking about the memory and CPU requirements for the AWS routers to recalculate those routes. It's going to get ugly really fast. And that's why they limit the number of routes you can give them. Now, the better your organization's IP addressing scheme, the smoother things are going to want to be. Now, on the internet, we get 900,000 routes from one ISP. We go to an internet point of presence and there's 20 ISPs in there. So 900,000 routes, 20 ISPs, 18 million routes sitting in the routing information base sitting on a router. That's ugly, right? Yeah, it's ugly. So now imagine it from the cloud provider. So the way we do our IP addressing determines if we can subnet or supernet or give us a clean environment. So Chris, if you want to show slide 17, I want to show you an example of a disastrous IP addressing scheme. And this is what network architects like me typically find. And it's because people don't understand subnetting and supernetting. And what happens is they're now designing an architecture and the architecture will fall apart. If you look at this particular environment, and there's only 4 subnets here, so it's actually going to hold up. In this particular case, in our data center, we've got 10.0.0.0, 10.0.2.0, and 10.0.3.0, all in our data center. Now, somehow, we also put 10.0.1.0/24 in the cloud. Now, right now, we're only dealing with 4 routes, so everything's going to be fine. But what if we were to tell the cloud that, well, actually, what if we wanted in our data center to send one route to the cloud provider, 10.0.0.0/22? Does anybody see a problem here? Well, here's the problem. 10.0.0.0/22 covers the 10.0.0.0, the 10.0.2.0, the 10.0.3.0, but also the 10.0.1.0, which is sitting there over in the cloud. Now, if we've got other routers in our network and on the data center, we say we have and we own 10.0.0.0/22, and that subnet's owned someplace else, now our traffic won't make it to the cloud inside of our network, which means all our cloud systems won't be reachable over our private network, and we're going to have a lot of unhappy people that can't reach the cloud. Lots of it. Trust me, you don't want to be in this position. So if we address this properly, the 10.0.1.0 would also be in the data center, not the cloud. So this is what's called, putting your subnets in the wrong spot. Now, Chris, can you go to the next slide for me? Now, this is where we had a network architect or a cloud architect that understands networking. Notice they used a different private IP address block for the cloud and the data center. So here we've got 4 subnets in the data center. 10.0.0.0/24, 10.0.1.0/24, 10.0.2.0/24, and 10.0.3.0/24. We can send the cloud a single route, 10.0.0.0/22. So now we've got 100 routes we can send the cloud provider, and we've only burned 1. Got 99 more to go. Now, how many routes do we need to learn from the cloud provider? Well, can we take 172.16.0.0/24, 172.16.1.0/24, 172.16.2.0/24 and 172.16.3.0/24 and send a single route back to the data center. There you go. Now in our data center, we get one route from the cloud. The routers in the data center, they're listening to Bob Marley singing No Woman, No Cry. They got their sunglasses on. They got a cocktail in their hand. They're all kinds of relaxed. They're not working so hard. And the virtual router in the cloud, they're listening to Ziggy Marley singing Beach in Hawaii, talking about Ujjayi breathing and yoga, which is part of that song. And those routers are all kinds of relaxed and chilled in the cloud too. So we got Bob Marley in the data center singing No Woman, No Cry. We got Ziggy Marley, rocking out or reggaeing out, if you want to call it that way, to Beach in Hawaii, and everybody's happy. And his kid Damian Marley singing about medication that makes him high. And, that's going on. And then Skip Marley's out there singing with Katy Perry, and all the Marley family is happy. No one's overworked. They're all chilled out, relaxed with their cool dude and cool lady sunglasses on, and everybody's happy. So that's why we're actually doing these things. Chris, you can take the slides off. So when we design an IP addressing plan, when we have to take, for efficiency purposes, what we're doing is we're taking a big CIDR range, that classless interdomain routing range, the 10.0.0/8, and then we're chopping it down into little pieces. And then from there, when we send the routing information to others, we try to minimize the routing information to what's necessary. And by doing so, we can minimize the workload on the routers. Now, in the data center, it's just good architectural practices to summarize your routes. But on the cloud, the routers are the equivalent of 1980s routers, maybe even 1995 routers, but it's really limited in what you can do. And it's not because the cloud providers are bad. It's not because the cloud providers don't know what they're doing, but it's scale. That's why you can build a higher performance data center than you ever could use in the public cloud, because you've got more control. That's why a private cloud will always be higher performance than the public cloud if you design it and build it correctly, because you've got more control. So when it comes to good architectural principles, part of what we need to design is private cloud, public cloud, hybrid cloud, multiple public clouds, combination of the above, but it all goes down to the same thing. What's in the best interest for our customer, and we have to plan it out correctly. So let's talk about a few other things, and then I'll answer any questions you have, and I'm going to give you some guidelines. If you need a router identifier, use a /32. 1.1.1.1 with a mask, 255.255.255.255. Pretty easy to remember. That's a public address. I don't use it, but you get the concept. For a WAN link, use a /30. 255.255.255.252. Why do we use /30s on WAN links? Well, you got a wire. You got a router over here and a router over here. You could only ever put two routers on a single wire, right? So we could only have two addresses, so it's not going to expand. For the cloud, our smallest subnet size is a /28. Guess what? Any place where we've got servers, don't make it a /28, make it a /24, because I promise you think you need 10 servers. Next thing you realize you need 89 of them. Next thing you realize you need 129 of them, and you're good to go. So for LAN links, I strongly recommend you use a /24. For LAN links, never go above a /23, because all systems broadcast. I'm here, I'm here, I'm here, I'm here, I'm here. And every time a broadcast gets placed on the subnet, every host, every server, every router actually has to see that broadcast. And if you want to know exactly how hard broadcasts are on the CPUs of the router, when I used to work in the financial space building trading systems before they adopted multicast, back in the days where we had single core CPUs, we literally were giving traders Sun workstations that had multiple CPUs. We maxed out the RAM, and we had to spend $20,000 per trader's computer just to have the performance to deal with the broadcast. Because as soon as we would send 1.5 megabytes of broadcast, which is nothing, today's gigabit Ethernet links could take a gigabit. but we were sending 1.5 megabytes of data via broadcast to these systems that were $20,000 each. Their CPU would be 75% just looking at the broadcast because they had to broadcast it. So that's why we've got to constrain our subnets to no more than 500 hosts, because broadcast can be very destructive to a network. So what did we talk about today? We discussed what is subnetting. We talked about what are classful addresses. We talked about what goes into subnetting. How to sub. We did some supernetting as well. We did some practice on subnetting design. In a few minutes after this, we're going to answer career questions. But before we do you have any questions on subnetting that me or Leo or anybody from my team can actually help you with? Because I want to make sure you had a great educational experience in today's Networking for Cloud Computing training, AWS Network training, What is CIDR training, and Subnetting training. Any questions, please let me know. And Mark, my great friend, my CCI buddy, who's helping me and us with many things. Thank you for your assistance in the chat box, as well as every other blue wrench that was in the chat box. Any questions from you guys? Any questions, everybody? Because I want to make sure you all had an incredible experience today and learned a lot. I started to see some answers in that chat box that were making me really happy, because I feel like a lot of you guys got a lot of education today. Ask us your questions. Now, while we're doing that, I want to thank Leo Paredes from my team for being Professor Subnetting today. Leo is exceptional in every way. I'm thrilled that Leo's part of our team and our students love him. Santabar's question. Okay, what if you had an odd number of addresses? How would you supernet? I'm trying to think of an environment where we would have an odd number of addresses, because everything is in the power of twos. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So it's okay. So Santabar, I think I understand your question. What would we do if we had like an odd number, meaning a 10.0.0.0, a 10.0.0.1, a 10.0, so a 10.0.0.0, a 10.0.1.0, a 10.0.2.0. So in that case, we have 3 addresses. Well, we have 2 options. We could summarize them all into a /22, in which case we'd be advertising the 10.0.1.3/24, which we may or may not have. So kind of that, it might be an option. Now, Santabar, if we have 3 addresses and we don't want to take the risk of advertising addresses we don't own, we'd summarize it to 2. So let's say we could do the 10.0.0.0/24 and the 10.0.1.0/24 and supernet that to a /23. And then we could leave the 10.0.2.0/24. And we could take those 3 addresses and break them down into 2. So Santabar, that would be the most correct. I hope that made sense for you. So we couldn't fully use that. We'd have to create 2 subnets with the odd number. But yeah, that's a really great question. Ritika, I'm so happy you said great session. Subnetting was never before so easy. I'm thrilled to hear these things. We're going to join you all in 15 minutes to answer any questions you have about building a great cloud computing career. Want to become a cloud architect? Ask me how. Want to learn how to get promoted as a cloud architect? Ask me how. Want to learn how to raise your salary as a cloud architect? We can really help you with that. Want to know how to win a cloud architect interview? We can help you with that. Want to learn how to become a cloud engineer, which is a completely different job than a cloud architect? Guess what? We can tell you how to do that too. So whatever it takes to build you in your cloud computing career. If you had fun, if you learned a lot, please like this video, subscribe to the channel, hit the bell notification, and give me a hashtag subnetting in the chat box. That way I know everybody's awake, alert, and oriented ×3. And I look forward to seeing so many of you in approximately 15 minutes on a career question and answer session, which my team popped into the chat box. Thank you, Chris, for being behind the scenes and doing all the work to organize Leo and me. Leo takes a lot less.
Somebody's got to do it. You can't do it yourself.
Leo takes a lot less organization than I do. We all are a little different. I'm like the Energizer Bunny, bouncing from idea to idea to idea. So we're always grateful to have Chris organize things. So you don't actually see the mic bouncing off the walls like my cat Cindy. No wonder we get along so well.
Yeah, and like Mike said, we're going to be, it's roughly about 15 minutes. We're going to be starting up a Q&A session for everybody. Join us over there if you've got any career questions, training questions, questions about us, questions about our program, questions about your career, your training, whatever it might be. Join us over there. We put the link in the chat box. It's going to be right here on our YouTube channel. So make sure to join us for that. Leo, you got anything to say?
Yes, I can't thank you enough for the opportunity. Mike, Chris, thank you everybody for participating. It was a real pleasure being here and contributing with making it easy for everybody to understand subnetting and supernetting. Thank you.
Well, thank you.
And Mike,
Ferreira, let me answer your question. Why would you use subnetting with IPv6? We have to use subnetting no matter what, because we can never have more than 500 hosts in a network. So we're always going to be subnetting everything in IPv6 or IPv4. And even in IPv6, if we didn't subnet it down, for example, we could be burning billions of addresses per interface, because that's 120-bit address in hexadecimal, which with IPv4, it's 0 and 1. With hexadecimal, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So imagine 16 to the 128th power. Imagine burning an entire network like that.
Wow. All right. And I'm going to put the link. Here's the link to our Q&A in a few minutes. All right, put that in the chat box again for everybody. So make sure to join us over there. I think Alonzo might be joining us. I'm not sure. He may have lined some calls up while we were on this, so I'm not sure. But join us over there for our career Q&A session. We look forward to it, and I know I enjoyed this session. So thank you, gentlemen, for doing this. Any last words before we end the live stream?
I'm really grateful for Leo to come here and share his time with you all today. I'm really grateful for all your participation. Tomorrow we've got a webinar. I hope you all attend. And then next week we've got a BGP information.
Thursday we have a webinar, not tomorrow.
Yeah, I'm sorry, Thursday we have a webinar. See, I'm so excited about this webinar and what's going into this that I keep thinking it's tomorrow because I can't wait for it. So join us in the Thursday webinar. Take care, everyone, and I'll see you in the question and answer session in a few moments.
All right. See you all in a few minutes. Go to that link that we put in the chat box. Thank you all. Bye.